All right, Arvind, I think we can get started with the session.
All right, so good afternoon. It's my distinct pleasure to invite Dr. Janssen, who is a group leader for material informatics in the Computational Material Science Department at Max Planck Institute for Eisenforschung. I hope I got it right. But before this, he was also a director's postdoc at the theoretical division of the Los Alamos National Lab, working on the development of autonomous simulation protocols for simulations on exascale systems as part of the Exascale Computing Project, or ECP. He's also the lead developer of PyIron, an integrated development environment for computational material sciences, a maintainer of over 650 open source software packages for the Conda Forge community, and a regular contributor on various open source projects on GitHub. So with that, I'd like him to start chatting about foundation models for materials discovery. And thank you so much.
Perfect, thank you. Good, yeah, we recently changed the name. So we did iron research for 100 years. We're now with the next 100 years of sustainable material science. So it's now Max Planck Institute for Sustainable Materials, but it was in April, so we just changed it. What I want to talk about is really this idea of starting with the atomistic structures and then using simulations to be able to predict materials really over the whole periodic table. And then from there, make the step, okay, what does it take to build a computer program that can do the prediction for us, right? So can we have an agent similar like a PhD student where we say, ask them a material science question and they do maybe some simulations and then come back to us and give us an explanation of how they see it, and then we have a discussion and maybe run some more simulation. Well, now it's switching. So what I, as a material scientist, really find fascinating is this idea of, if we take one element, let's take magnesium here as an example, right? So which is super light, but unfortunately rather brittle, right? So you see this here already at 10% compression, we find that it becomes brittle. But then we take just 1 weight% of aluminium and a tenth of a weight% of calcium, and we get this highly ductile alloy, right? So you can compress it up to nearly 50%. So by just changing a little more than 1% of the overall material, we get drastically different material properties. And so we want to design models that can find these special alloying compositions over the whole periodic table. So we can just make a quick estimate, right? It's like we just like a back of the envelope estimate. We can think about, okay, we fix magnesium, we look for a 3-component alloy. Maybe there are roughly 70 elements that we want to consider. So that's roughly 5,000 different permutations. We then try, let's say 10% concentration steps, 20 different temperatures. That's already 1 million experiments. And so when we see the first challenge there, it's like to address this chemical complexity is very challenging experimentally, and then even for simulations, handling 1 million simulations is very demanding, right? And not really possible with today's tools. Then the second challenge in material science is really this intrinsic hierarchical nature of materials, right? So here I just show it of the different kind of simulation methods, where we start with the finite element at the top scale, then go down of the grain boundaries, the segregations, really coming to the crystal plasticity and the structure dislocations. What I will show in the following slides is really that we start at the atomistic level, where we start with the density of our electrons, and then see how far we can push this bottom-up approach to really address all the other scales and make predictions on the larger scales there. Right, so the second challenge that we face as material scientists there is really this hierarchical approach. And is this something that we can teach to a foundational model or for a foundation model, and what is required there to make it understand the hierarchy of the different methods? And then obviously there's this question of like, how precise is our prediction, right? So when I do simulation, is this really something that we can leverage and compare directly to experiment? And here I just show the heat capacity for calcium as one example, which we calculate over temperature. And we see that for 2 theoretical models, one's the generalized gradient approximation and the local density approximation, both coming from density function theory. We find this very nice agreement for the low temperature FCC phase. And then for the higher temperature BCC phase, we find this agreement with this lower branch, right? So all the dark symbols, those are all experimental results. And so this is important because previously databases that were used on these larger scale models really relied on this upper branch. And only by producing these theoretical predictions and really showing this one-to-one agreement with the experimental results, really starting from the predicting basically just the interaction of the electrons, right? So like going from there and predicting material properties that can be measured macroscopically, we were able to convince them to update the database and now also follow this lower branch, right? So we are now really at the scale where we can use these ab initio thermodynamics models to really make quantitative predictions of material properties and no longer just qualitative predictions. So we can really use simulation as a tool to make prediction, and that's why I'm so optimistic for building foundational models, which really then control simulations to maybe answer our questions and reason based on these simulation results. Right, and then how is this done? Right, it's like you could do this by just brute force iterating over the calculating all the vibrations and really trying to get the thermodynamic stability of a phase. But what's typically done is really using much more efficient approaches, right? So what we do here is like an adiabatic approach where we first look at the vibration of the crystal lattice, then maybe consider the electronic effects of the temperature, the phonons really having the vibrations of the nuclei, and then finally at the last step, we use thermodynamic integration, really going from the approximative model to the full anharmonicity. And basically at this stage, if you have a bad model, we would need still the same amount of steps as brute force sampling, because we usually find very good models. We can really reduce the sampling steps by orders of magnitude. And so now if we look at this, while the first two methods are typically available in standard DFT codes, these later two require additional codes, right? So like there's phonon codes to get the final temperature vibrations. And then to do this thermodynamic integration, we would do like fitting a machine learning potential and then do the integration between the DFT and this potential using a specialized code. Right, so the third challenge that we find here is really having efficient sampling approaches to be able to really address this part. And so I think we as computational material scientists really see these challenges, and we, I guess, can solve them step by step by producing specialized tools. So what I want to do now in the next few slides is a bit give an overview of where we're standing and what are the kind of methods that we would like to teach a foundation model to then help us on this kind of research, right? So really can we open this up to really have the model assist us in our day-to-day task really as an assistant on the work that we do. But yeah, if there are any questions in between, feel free to interrupt me. If there's anything that was not clear or you want to have more explanations, feel free to just maybe raise your hand or unmute yourself. Okay, then I just continue. Good, and I guess the most prominent example at the moment in our community are really these kind of machine learning potentials, right? So Ian already talked about this as he talked about the maze model as one example. They're typically trained on databases of interatomic structures, and we have a fitting step, and then finally the validation of calculating our final temperature properties. And so just in terms of their construction, what they achieve is this linear scaling with the system size, and that's done by using a cutoff radius and the local approximation of the interatomic environment. And then there are different kind of descriptors, moment tensor descriptors, the snap descriptors, embedded atom method, or the atomic cluster expansion that Ian was also referring to. And these descriptors can then be combined with different kind of models, right? So we can have like a simple linear model, a Gaussian process, or a neural network. And so you see already here that we can have a wide variety of different models, and depending on the kind of application, we can really design application-specific combinations of those, right? And that's a project that we did together with the colleagues at Sandia National Lab, where we used the FitSnap code really as a framework. It's directly integrated in the LAMMPS code to be able to construct these application-specific machine learning potentials and really have this kind of flexibility. And that's also what we want to see basically for the models to be able to teach them these kind of methods, right? So be able to do complex processes like the fitting of a machine learning potential should really be possible directly from the foundation model to have the ability to really run the simulation, get a new insight, and then derive the new material property and do the next step. And so let me maybe just go through the individual steps in a bit more detail. If we start with the data set, we first thought that, okay, if the data set obviously limits the predictive power of our model in the end, right? So if we have a domain expertise set, as is what's typically done, we already introduce a human bias to our model. We're just teaching it on one specific area of material system that we already know, and therefore also somehow limit the prediction that we can have. And so what was done in Los Alamos is really this idea of, okay, can we invert this process by maximizing the information and entropy of our descriptors, really spanning the whole space of different configuration that the descriptor that we use, our local approximation, can really cover. And that's what's shown here in green, right? So we can really cover a wide range of different configurations. I also show this now in terms of the descriptor space of these individual parts. And you can see it also as like one atomistic configuration, right? So like the first part here really is removing the bias of like a human specialized data set, which would then also reproduce just the data that we put in, right? So if you have a bad input, a bad training set, or a limited training set, also the predictive capabilities of our model would be limited. Right, so by maximizing the entropy, we really get a highly diverse set there. The challenge with this set is then that while many of these potentials are very good in when they're trained or when they're validated on like an expert set, so on the typical set that I used, the same models achieve much higher RMSE value when they're compared on this much more diverse set. Right, so we really see this challenge that it is possible to build models for this highly diverse sets, but it's much more challenging and they are not as precise than the more specialized expert sets. Right, and then raise the question, okay, what can we do to really go one level deeper, right? So what is required to also get the quantitative predictive capabilities on these more targeted sets? Right, and then we just did this here for two elements. We looked at tungsten and we looked at beryllium. And what I want to highlight a bit is like the amount of calculations that are required in these kind of models, right? So like we had this discussion before, okay, can we just train all this data to the model and just give it as like an input for our foundation model? Or is it maybe better to have the foundation model be trained on some kind of coarse-grained or more abstract parts? And that's what I want to show here, right? So like really learning from the large data sets, reducing them stepwise, and then provide these coarse-grained models as interfaces to our foundation model. Right? So we started with 40,000. We then vary a bit the DFT precision and see, for example, that the optimal cutoff radius that we choose to achieve a certain RMSE really drastically changes when we go to this more converged DFT calculations. Right? So having a smoother energy surface, having more plane waves to describe our energy surface results in a data set where it's easier to fit a potential. Good. And now obviously they raised the question, okay, why is there the difference between the elements, and why is it so much easier to fit a data set for beryllium versus fitting it for tungsten? And what we did there is we really just looked at the distribution of the configurational energy, right? So it's, I guess, very clear to all the people with a machine learning background, but like just saying if you have a very narrow distribution in your data set, then obviously you also achieve a very small error that you can, or predictive capability. But if I now stretch my distribution like we do it here in green for beryllium, we can make it as hard to fit as the tungsten data set. And so while this might sound very simple, I guess it was a long-standing issue in our community that people just reported the RMSE value as a performance of their potential, but never really referenced this value in comparison to how diverse the data set is. So it's very easy to have a small RMSE value on a very narrow data set, but when you have a widespread data set, it's much harder to get this kind of optimal performance. And so that then got us started to think a bit more, okay, what kind of models do we need to quantify the precision of the underlying data, right? So like if we want to make our predictions finally to macroscopic properties, we have to be sure that we are quantify the uncertainty during our calculations and how it propagates through the different models that we have. Right, so here I just show this in terms of the bulk modules from a DFT calculation and how it changes over the energy cutoff. And the energy cutoff just limits the number of plane waves that we can use in our model. And so we can obviously always compare to experiment, right? So that would give us our level of accuracy. And that's going to be hard to control because we can't really change the approximation, basically the interactions of our electrons. But what we can control is really this level of precision, right? So by choosing a finite basis set, we always limit the precision of our model and therefore restrict in a certain way the optimal resolution that we can have, right? So really the distinction between accuracy and precision, being able to see, okay, what is the optimal way we can optimize our model for, right? And all these things are, again, parts that if we want our foundational model to make simulations and then interpret these simulations, all these lessons that we learned as like students from the very beginning is also something that we either have to teach the model, or well, what we want to advocate for is really automate the small parts one by one and then have the model really interact with agents that can already address this one challenge. Right, so in this case of DFT convergence, we now spent the time and really did a full sampling of the energy cutoff and the K-point mesh. So 2 parameters were describing our uncertainty, and then we compared it to the value for the bulk merge that we get at the highest level of convergence. And to sample this kind of landscape, we used typically 50,000 calculation if you would just naively do this kind of part. And what you could show is that it's possible to predict exactly the same surface by just a fraction of this calculation, right? So just 4,000 calculation, or more than an order of magnitude speed up to get this kind of insight. And what we basically did there is like a tensor decomposition, right? So what we found is that when we can basically look at this in terms of like a cube. So where you have the K-point mesh on one side, the energy cutoff, and then the volume. And then in this cube, we only look at the edges, right? So like one edge at the maximum K-point mesh, maximum energy cutoff, one at the minimum one, and then one where we only increase the energy cutoff or only increase the K-point mesh. And if we look at these 4 curves, we can find that always, if we fix one parameter and just look at the difference between the other curves, there's not so much a coupling between the 2 parameters, right? So we find a systematic contribution from the energy cutoff, a systematic contribution from the K-point mesh, and then if we take the difference of these differences, right, so we find there's a remaining statistical contribution. So you see that this tensor decomposition basically allows us to describe all the data in this cube by just looking at the 4 surfaces, really constructing any point based on the precision of the maximum point, and then two systematic error contributions, and then an additional statistical error term there. All right, and then we combine this and really get these predictions. So here we now look at the systematic error and the statistical error, and for aluminium, you see that the statistical part is really not so relevant. But then if we go one step further, right, so we take copper here as an next example, we see that those errors are more equal, right? So we have that they really come to the same level. And so if we now combine them in one plot, we can basically draw this what we call then the error phase boundary, right? So the area where we switch from the systematic error being dominant in the top corner to then the statistical error being dominant in the lower range. And by having this kind of understanding of which error is dominant, we can also decide which parameter to optimize next, right? So that it makes no sense in this lower area, we always have to optimize both the energy cutoff and the K-point mesh. Well, as soon as we reach the area where the systematic error is dominant, it's sufficient to optimize one parameter. And so it's really like for the different areas, we have different levels of convergence. For the statistical one, multiplicative, and then for the systematic one, additive convergence. And now to show that this model of approximating the uncertainty and propagating this really works, we did a study over the periodic table, and I just show a couple of elements here, right? So we can now see, if we go, for example, from calcium, aluminium, and then copper, silver, gold, right? So we can really see the trends and study the trends, how this can be combined. And that will really be the hypothesis, right? So like, rather than teaching or letting the model itself discover all these relations, maybe it's easier to have like agents that are specialized for these parts and say, okay, the agent, and like I can do here, right? So I can now ask a question, what is the calculation that's required to get the bulk modules with a certain level of precision. So I give the precision already as an input, and it can then, using the schema, identify the area and identify the convergence parameters to achieve this kind of calculation. And really having this part encapsulated and really solved step by step. Good. So the next part is now taking this forward, right? So now we have the optimized DFT data. We can also apply this then for the machine learning potential and see how we can. Yes? Was there a question or?
No, nothing that I can see. Maybe
okay, sorry.
background noise, sorry.
No problem. Just feel free to interrupt me, right? So I'm always happy to adjust this.
Yeah, and maybe now that there is an interruption, I'll just ask a couple of questions. This is super interesting. Do you imagine that there is obviously there's sort of the downstream application, right, where you take this data and then fit a machine learning potential. But do you imagine that there is a way in which we can incorporate this fidelity already in answering? So you talked about sort of the precision of that answer, but then, frequently, right, we're not just actually interested in the precision of that one answer, but, trends across a bunch of different materials and like trying to solve the ordering problem of, material A is better than material B is better than material C. So any thoughts in that direction?
Yes. So that's really the idea, right? So we now did this for one quantity, that the bulk module is really over a wide range of materials. And what we're now looking into is how much are there trends, right? So like, do different properties scale in the same way? So the hope would be that you have a subset of small quantities and they have the same convergence behavior as much more complex quantities. So you would study it once and then know the relation, how the convergence of different property changes. And then basically the next part is really how does it affect now for multi-element systems? That's something we haven't solved yet, but it's definitely very interesting.
Yeah, this is fascinating because what you actually are advocating, which, I hadn't sort of thought about it in this way, right, is there's a simulation agent, but there's also a fidelity agent, right, that sort of is deciding so that you can sort of separate the two in a sense, right, that you don't need the two to sort of be the same. You can have something that generates the code and the workflow, but then there's some other agent that sort of is this foundation model for sort of accuracy or precision, different kinds of calculation parameter settings and things of that nature.
Yes. So like I said, like our question is a bit like how much of this are really separate models and where is it maybe more efficient to understand the topic and then develop specialized agent, right? It's like this agent can also be like an analytical model or like a coarse-grained model to just make this more efficient until we have already the very general foundation models that we can use for any kind of application.
Yep.
But I think like to benefit from the knowledge in the community, to benefit from all this expertise, what we try to now to find is really tools that work on autopilot. Right? It's like previously, every student would do convergence tests for their material system. Now we try to find ways to like automate these convergence tests and just say, okay, you give it in a tool, you give your computation budget, or you say, what is the level of precision I want to aim for? And then it chooses the right convergence parameters in terms of like, how many plane waves do you need and what kind of mesh density do you need for in terms of the K-point mesh?
Yeah, amazing. Good.
Then, yeah, we do the very similar stuff also for the potential. Here we now look at the RMSE again on our y-axis, and then the cutoff radius and the number of parameters. And again, you see already here, right? So we benefit from having a large number of calculations. So I took 26 different J2 max, so that's our scaling parameter for the snap potential, and then 31 different cutoff radii, just to see how the scaling depends. And the first thing that we find is that basically the more flexible your potential, the more freedom you have there, the larger you need in terms of the cutoff radius. And that's already for our community, again, was a very important insight, because previously people chose the cutoff radius based on the radial distribution function, and basically the nearest neighbor distribution of the equilibrium lattice and just saying, okay, how large does the cutoff have to be there? But what we find now is basically it's much more of like a numerical parameter. If you increase the flexibility, if you increase the number of parameters that you have, you most likely also need a larger cutoff radius. In the same way, then also the computational cost scales with the cutoff radius and the number of parameters. Right? So that's what we show here. Once in terms of like nanoseconds per day and hours per nanosecond, where we again can see that there is an impact of the cutoff radius, in particular for small number of parameters, that's rather drastic. But the much more strong impact here is the number of parameters. So what you can learn from this plot is basically whenever there's a chance to increase the cutoff radius, but decrease the parameters to achieve the same level of precision for your potential. It's more beneficial to use a larger cutoff radius, but a smaller number of parameters to describe your potential. Right? But like, it's really key to not only think about precision of our potential, our application, but then also consider the computational cost, right? It's like, what is the impact of this potential if we then apply it for other simulations? What are the options that we have if we, in terms of the computational resource we can use? So now it's the same graph as before. The only thing I changed is now the coloring on this color bar, right? So this is now the computational cost. So if we pick one line and we follow it from right to left, we see that it becomes more, goes more towards darker colors, right? So it's computation more efficient to go there. And we can now use this kind of a representation to draw a Pareto front, right? So this is the Pareto front where for the least computational cost, we can achieve the lowest RMSE value, right? So like, what is always this relation? What is the cheapest potential we can use to achieve a certain RMSE value? And if we just plot just the information here now over the computational cost, we can see, okay, it may make sense maybe in the beginning to increase this, but in the end, we have to invest more and more computational resources to get just a little bit better. And you can say, okay, that's a very general insight. Why is this important for my particular project? Previously in our project, people used a potential which was nearly an order of magnitude, so it was, I guess, about a factor of 8, more expensive than our optimized potential. Right? So again, what I want to highlight here is that if we have access to a lot of data and if we have tools which can generate this data, we can find much more precise quantities, and this really has like nearly an order of magnitude in acceleration for our performance, right? Really being able to study totally different systems by having this level of flexibility. Right, so the cutoff radius really here being primarily this numerical parameter. We then moved on and changed our basis set. So from a linear description of the SNAP descriptor, we now went to a quadratic approach, and we can basically do the same story here, right? So here you see for the RMSE, if you want a very efficient potential, there is a certain regime where like the linear model is better, but then because just calculating the quadratic terms is very cheap, much cheaper than calculating a more complex linear potential, we see that the red line of our quadratic potential is crossing this, and you can really see how this Pareto front forms over the complexity of the potentials as well, right? So I think in addition to considering the uncertainty, in particular when we have these more complex simulation protocols and we want to apply these potentials afterwards, we also have to consider what is the computational cost and how much can we really afford these calculations in the next step, what is required to do the next step of calculation. All right, and then we can move on and include more quantities. So here we now switch from fitting to energies and also include the four.
Yes? Yeah, and we have a question, yeah.
Sure.
I'm back. This is really cool. How sensitive are these plots to the actual hardware being used? Okay, so I'd imagine that like on some level, like a switch from like a GPU to the or CPU to GPU would matter on like the particular cost curve. But do you also have like sensitivities to like whether or not you support like AVX 512 like vector operations or just standard CPUs or is that just like yeah?
I guess so we didn't do it for the specific vector operations. What we saw, so like the SNAP potentials were also part of the exascale project. So in the exascale project, we optimized it for different GPU architectures. And we definitely see that the bandwidth of the cache on the GPU die is very important, right? So like, I really want to saturate the whole memory of my GPU. So really have like several thousands of atoms on one GPU. if your system is too small, you're wasting resources. If your system is too big, you always have to move them out, or you can't go to such complex descriptors, right? So there's definitely like the main factor at the moment is really the memory bandwidth and how much memory you have on your GPU. If you have more memory available, you can, or somehow intrinsically, the complexity of your descriptor is limited by the memory size of your GPU, or you have to use less atoms on the GPU. Does this answer the question?
Yeah, that's interesting. Do you have like almost like a roofline plot then for this? Like it seems like there's another dimension.
Yes, I don't have it, but
Okay.
there are definitely these plots. If you look for the people from Sandia, so the LAMS simulation code, they definitely did extensive studies. I'm not sure how much of this is published.
Okay.
The GPU companies were a bit restrictive of what we can say about their hardware when they're yeah. So I won't make any statements, but there are specific GPUs which have larger memory buses and others who have smaller ones, and then they claim to have a lot of performance, but then when you bring them to the test and run them next to each other, you don't really get as much flops as the hardware promises to have. Which is then it's like the question of like what is a flop and what is the performance of a hardware and what is the cost that we are willing to pay for it is then very application specific, or can you really, how much can you fine tune for this interface? That's still a challenge that is not really solved there.
Thank you.
Good. Yeah, and so we really see here that it makes sense to do these automated studies and really have all this data available. And what our goal is now really, can we automate this, right? So now I want to take the third part is really now looking into how this affects if we go to the thermodynamic properties, right? And here I just show how we calculate the melting temperature now for one of these potentials. And we do this by using an interface approach. So we have a solid sample and a liquid sample, put them next to each other, and then see how this process can be automated. And before, this was a very delicate task. It really that could only be done by people who had the expertise, because they really had to figure out, okay, how do I relax the system so that the interface doesn't fracture and I don't compress it too much, so that it either becomes fully liquid, or if I relax it too much, it becomes fully solid, and so on. So people really struggled with this kind of automation. And we then use our Python framework to really structure this a bit, right? So that we have certain user inputs. The user just select the element, the interatomic potential for this, and then they can provide a guess for the melting point. If they don't provide a guess, we just choose the experimental melting point. We then start by heating up our structure, fixing half of the structure, continue heating the other half to really have this nice solid liquid interface. And then we apply strain orthogonal to the interface. And then first run a volume and temperature constraint simulation, followed by a volume and energy constraint to really get this very nice curve of like how the temperature changes over pressure, so that at zero pressure, we can read our melting point. And then we use this melting point and provide it as another guess for this iteration. What we could see there is that we had to extend a couple of the existing tools, right? So here I show the common neighbor analysis, which is typically used to identify structures. And we see that it only predicts roughly 20% to be solid. But when we as humans look at the structure, we clearly see that it's more close to 50% that is already solidified. Right, so that really shows us that there is still a wide range that we can use, and we were able to do this by using a kernel density score. And in the same way, we struggled with having voids in the structure and getting this basically no dependence in terms of like the strain over pressure. And again, we could address this by optimizing this and really having this kind of nice part by identifying where there's a void formation in the liquid part. And again, all this is just to be able to then afterwards really screen a large set of the different potentials. Right, and that's what I want to show here. So we just iterated over a database from the NIST, National Institute for Standards, right? So like we choose 200 potentials, took 260, and then calculated the melting points for all of them. For some of these potentials have more than one element, so we calculate 260 melting points. And the important part here is really that we find this kind of spread of up to 1,000 Kelvin, right? So like there's a wide spread in these potentials, and that was really the risk that we face, and why we believe these kind of automated protocols for individual steps are necessary to really accelerate the screening there. Good. I have 10 minutes left, right? So I would maybe accelerate a bit and skip a few slides. Just very briefly, we are now moving all this to be able to do it also for the phase diagram. We are not yet completely there, right? So we can predict phase diagrams for machine learning potentials. It's more at the moment of a qualitative agreement and not yet at the stage where we can really get the quantitative agreement. But these are the kind of tools where we think, okay, if a simulation agent has access to this and be able to get phase diagrams directly from simulation, it's maybe a very amazing tool to then discover new materials. So let me then quickly come to the technical part and really see how we integrate this in our framework, right? So like really now going more in terms of like a hands-on perspective, what is required to do the simulation and what do we currently teach our students and what would we like to teach to also then to a large language model. And so the goal for us was really, can we, and this development started when we were still using primarily the terminal to run our simulations. We were wondering, how can we make our workflows more easy? How can we make them more accessible? At that time, really with the idea to make it easier for students, but nowadays the same applies also to make it easier for machine learning models. Right, and first inspiration there being, for example, SciPy. SciPy really nicely wraps all the numerical recipes in like a very standard Python interface. By changing just a single variable, we can easily switch between different minimizers. So the same is something that we would love to have for DFT codes, right? So switching a system that we want to study from one DFT code to another by just changing a single variable. The limitation with DFT, as we heard already, right? So like we need computing resources like exascale or large clusters to really run them there. And so there we also need to have the ability that from the Jupyter Notebook or from a Python interface, we want to submit the calculation, execute it somewhere else, get it back, transfer it, and have all these kind of interactions all controlled from the Jupyter environment. And then finally, the extendability, right? So the code should be reproducible. We would then want to be transferable, so applying the same kind of code to different kind of systems. And then ideally, we also want it to be extendable. So if I now develop a new method, maybe a new minimizer here, I want to be able to put my minimizer into the existing workflow and just see what is the effect of this minimizer. And so from these challenges, we really found that we want a tool that separates the technical complexity and allows the user really to primarily focus on the scientific challenges. And this is where we really started with the parent project. And it was really inspired by what we see also from our experimental colleagues, right? So this idea of being able to look at an atomistic structure, maybe write your outline, what kind of simulations you want to do, and then run the full simulation. I guess in the interest of time, I skip a bit ahead, not looking at too much of the technical details. And I would then come to how we go from this more human-centered interface to then also to bring it to the connection to the foundation models, and then have a few minutes for discussion. Right, so like we were always motivated by this idea, can we make these kind of programming interfaces even more simple, right? So you saw the parent interface being Jupyter Notebook based. Before we had like a graphical interface based on like a Qt framework. And we also played around with visual programming prototypes, right? So thinking about how can we leverage those. But the development of the graphical user interface always took too much time, and the scientific insight that we could gain from there were very limited. So that was really where we get very interested into the large language models. And as Ian already said, right, so the project during the hackathon organized by one of his group leaders really finally gave me the time to work on this. So that's what's now called the Janssen project, which is a first version of an LangChain agent directly interacting with the simulation codes. At that stage, we used the ASE code to really run simulations, get an answer, and have a direct conversation with us. Right? So I show this here. You can load it inside your Jupyter environment. You can ask it a question, and you can calculate material properties. You could... Okay. And then you can compare it maybe to experimental results. Sorry, what's a question?
No, go ahead.
Okay, sorry, I have some feedback on. Right, and the important part is that during this part, while the experimental one is really just a lookup of data from a data source, like in this case, I guess Wikipedia, the first part is really running simulations. And so if we look into the code and we enable our debug mode, we see what's happening, right? So it's starting an agent. The agent first that knows the mapping, right? So it knows, okay, when we talk about noble metals, that's gold, silver, and so on. So it starts with gold. It then tries to identify what is the equilibrium structure. It has access to a Python function that can calculate or can return the equilibrium structure from a database of known structures. So it figures out that it calls the structure. It knows to use the chemical symbol. This is like the input defined there. And it knows then when I want to do this for gold, the chemical symbol for gold is AU, right? So like we do this, we get.
Yeah, and is this working on top of Llama 3 or is it a GPT-4 or?
This works with GPT-4, GPT-4o, and the Anthropic ones. We haven't gotten it to work with the Llama model so far.
Okay, thanks.
Did you, Llama 2 struggles. Did you try Llama 3 or did you not try it yet?
We tried, so there was the Gronk service. They have like 2 Llama models, I guess one with 70, or the 8 billion one and the 70 billion one. Publicly hosted ones. I'm not sure what their status is, but those don't perform so nice. So in the background, we use LangChain, and LangChain wasn't able to read the code there. Or at least I wasn't able to get it right.
Yeah, lots to tease out in the computational science agents hackathon, right?
Yeah,
so
this is next week.
This is really brilliant, right? So this is exactly the direction we need to go.
Yeah, so that's why I thought I think that for us the important part was really if we can find these kind of small tasks that we can automate, write tools like develop coarse-grained models, and then have the large language model really interact with these coarse-grained models rather than trying to teach it everything. That's the direction that we are currently following. So yeah, well, what I just show you, it calls these functions, it knows the input, then it gets the equilibrium structure, and then it takes the structure and does a simple structure optimization, and afterwards computes the bulk modules. If we now look into what is required on the code side to realize it, we can see, and I just show it here for one function, but all the code is all available on GitHub. So feel free to take a look. We're very open. We try to share the expertise that we gained so far. So it's really a lot of fun to work with this, and I guess we were all new to this. And then the code part here, the way we see it, basically coming from a programming background, is that it can basically be thought of like header files in C++ programming, right? So like we take a regular Python function, we have to be explicit about the types, and these types have to be somewhat represented as strings so that they can be communicated to the large language model. And then what we provide as a doc string is the information that the large language model uses to understand what the function is doing. So we primarily just followed the tutorial from LangChain to develop custom agents, and it was rather simple to integrate a lot of agents. To then be able to really call these kind of simulation codes and run the simulations with them. Yeah, so just as I said, what we see now is a bit of like the next question is really language the right way to communicate these kind of simulation workflows? Or are there other ways? For example, we're currently experimenting a bit with like graph-based structures. So can we represent our workflow, our scientific understanding of different steps as a graph, and then give this graph to a generative model and have the model find new structures inside this graph? But that's just an idea, maybe more of like an outlook. I don't have any results yet, but that's something I'm very curious about, to think in this direction as well, to like, how can we accelerate this process? And with this, I'd like to conclude. I hope I was able to give you a rough overview of what's happening in terms of like foundation models in materials discovery. Talked a bit about the success of machine learning potentials, how we use the Python framework to really be able to very quickly build huge data sets, in particular very targeted data sets, and then this new direction of like coupling it to generative models and building workflow graphs there. And with this, I'd like to thank you for your attention.
Thank you very much. So one quick question, have you looked at Lang graph?
Not yet.
Okay, so I will drop a link in the chat and yeah, take a look. It's very interesting.
Thank you so much.
Yeah. Any other questions online or in the room for Jan?
Good question here.
Yeah.
So how is error handled? Basically, like mostly two type of error. One is, say, if the agent is generating some sort of code, and then the code it generated is has some error in it, either runtime or compile time error. Or say there's the code runs, but the simulation package returns some error. Say if the potential isn't good, then you may encounter loss of atom error or some other like doesn't converge issue. How does this line of work handles those kind of error?
Yes. So I guess I can answer both on this example, right? So like the first part is the foundation model doesn't generate the functions. We as human provide it with the functions, right? So we select functions that we want the large language model to have access to, and then just mark them in our code with this tool decorator. With this, we get this deterministic approach, right? So it's really, we mark which functions are available. What the foundation model then does is like, how can it combine the functions based on the types of input and outputs that these specific functions require or produce. And then the second question of like, if your calculation fails, we see this here, right? So if the reference state is undefined, we return an error message that then the large language model can understand, right? So like, if there's an error message from your DFT code, you have to catch it inside your function, and you would just return a message and say, okay, this calculation failed. Maybe try with different parameters, or just say, okay, this is not possible to be calculated.
So the agent won't handle it. It will just pass it back to the scientist.
It passes it back to the foundation model, right? So like my agent is really this kind of Python function. It gets an input of like okay, for this structure, can you find the equilibrium structure? And it says, okay, either I find one or it doesn't find one. The foundation model could then potentially also call a different source of truth, right? So it could say, this agent wasn't successful. Maybe I have a different database I can ask for this information.
Gotcha. Thank you.
All right. Thank you very much. And yeah, I'm very much looking forward to seeing you next couple of weeks here.
Sure. I look very much forward for the discussion. See you around.
Thanks.
Thank you very much.